Convection. Convection. Okay? A hot air balloon is convection. All right? You heat the gas, and then the gas actually becomes less dense, which forces the balloon to rise. Okay? If you cool the air by turning the flame off on a hot air balloon, the cool air actually becomes more dense and causes the balloon to come down. But a hot air balloon rises and falls by convection. All right? Now, I think it was Bree in Virginia, if I remember right, that asked me about the marshmallow above the flame. They clarified that it says above the flame. So it is what? Radiation. Now, if you're one of those people who put your marshmallow in the flame because you like it charcoaled a little bit, that would have been what? That would have been conduction. Okay? But it's above the flame, so it's radiation. All right? Now, what describes the amount of heat an object has? It's size. So you could have said size or what other word would be good? Mass. Either one. You could have said size or mass and your answer would be correct. All right, number 3. What describes the motion an object has? Temperature. Temperature. Temperature describes the motion. All right. What does a very small specific heat tell us? Cools or heats quickly. Is correct. Okay. Now, number 5. You're going to look at the 2 cups at the bottom, and there's 3 questions in number 5. So, which cup has the least motion out of those 2 cups? Who has the least motion? B. Why? Because the temperature is less. Okay. And which has the greatest heat? Why? It has more mass. It's got a bigger size. It says 325 grams. Okay? Any questions about the open? All right. Find your notes. Because we got to talk notes for probably about a half hour.
Yeah.
Sorry.
Yeah, sleep.
Then put your head down and go to sleep.
Hey. Hey, Logan. You said throw it away. When you dressed up, you said throw it away. So I did. When you dressed up, yeah, you said throw it away. So I did. You have the one that you redid.
Are they the same notes from last time?
They're a continuation of.
You said you're welcome.
All right. Everybody got where we were last, what was yesterday? Tuesday and Monday.
Yes. Mom said, you read up amazing. No. No.
All right. So on Monday, we there? So on Monday, we talked about phase change, right?
Yes.
You got our notes? Particularly those of you who write slower. You need to get yours out so you're ready to go when the rest of us are. All right? So we said on Monday a phase was what?
It's a state.
It's a state of matter. So what were the states of matter?
Solid, liquid, gas.
Solids, liquids, and gases, right?
Yep.
So we said a phase change was going to be what? From one state to another. So an example of a phase change would be what? What was an example? Changing from a solid to a liquid. Anybody remember what that was called? Yes. I thought you might remember. A liquid to a gas would be another example. Anybody remember what? Gas to a liquid. Anybody remember what any of those things are called?
Vaporization.
All right. Which one is vaporization? From a liquid to a gas is vaporization. That's good. So does anybody remember what solid to liquid is called? Melting. Okay? We're going to talk about those today. Now, a lot of you remember the names, but a lot of us don't know this last part. So the thing we talked about at the end of class is what's needed for a phase change to occur. We have to talk about whether heat is absorbed or heat is released. Now, we finished class by talking about the fact that temperature stays the same. So I put an example on the board before we left, and a lot of people had written this down, but I put ice to water, and I put water to ice, and I said, what temperature does ice change to water? And you guys said what? 32 degrees Fahrenheit. And what's the Celsius temperature?
0.
Okay. And then I said, what temperature does the water change back into ice? And you said it was the same temperature. So I said, the thing to keep in mind, and I'm going to say this lots today because we're going to talk about a graph and we're going to illustrate it on that too, is temperature doesn't change. So the part that we're trying to figure out in all these phase changes today is whether heat is absorbed or released. And I gave you 2 vocabulary words that you should remember from biology class. One is called endothermic and the other is called exothermic. So 2 of our processes today are going to be endothermic and 2 of them are going to be exothermic, okay? And that's what the lab that's over there behind Alexis is about today, is endo and exothermic. Now, did we start talking about, and I marked this out and wrote 4 here, did we start talking about any of the 4 phase changes before we left on, all right, we're going to talk about vaporization. All right, so I'm going to skip melting and freezing for right now, and we'll come back to those, and we'll talk about vaporization. All right, so vaporization includes, first of all, both evaporation and boiling, okay? Now, before we get to talking about how they're similar or different, and I'll come back to that, we need to talk about, first of all, what they start as and what they finish as. Jacob, put it up here on my desk. All right. We also need to think about what they do with their heat. Do they absorb their heat or do they release their heat? So, to give me a little more space to work here, because normally I do this with melting, let me just put in a page. All right. We know that when we evaporate or boil, we start in the liquid state, right? What state do we change to?
Yeah.
We change to a gas. So I want you to envision something you probably learned in middle school. When you talked about the states of matter, somebody probably drew a picture for you and showed you particles in a liquid, and they showed you that the particles in a liquid were very close together. Not as close as a solid. That is correct. In a solid, they'd be touching. They'd be so close together, they wouldn't be able to move around each other. Now, when they change to the gaseous state, how do they compare? What would a gas look like? They're all over the place, but they're particularly much further apart, right? So, the question becomes, how do we change from a liquid into a gas? Do the particles have to become further apart or closer together? Okay. So we want the particles to move farther apart. So when you're trying to figure out if heat is released or absorbed, this is what you need to think to yourself. Now, as I look around the room, I've got at least 2 people I see who have earbuds in. Are we supposed to have earbuds in? No, that's not my rule. That's Miss Curry's rule, okay? So we need to take those out, all right? A, if they walk in, you're going to lose your earbuds and your phone, which really doesn't bother me because it's not my earbuds or phone. But knowing how dependent you guys are on those, I would hate for later today you not have your earbuds or your phone. All right? I know how dependent I am on mine. It would crush me to go home tonight without mine. Okay? And I'm 49 years old. I can't imagine being y'all's age and not having one. And I don't have mine in my hand 24/7. Now, if we want our particles to move faster, what do we have to do to them? What have we learned about heat that we have to do to get those particles to move faster? We got to heat them up, okay? Okay. So if we want them to move faster and farther apart, we got to heat them up. Does that make sense to everybody? Exactly. if we want to heat them up, how are we going to get them? Heat them up. Are we going to add the heat to the left or to the right? Well, first of all, here's 2 vocabulary words for you. That you should. Why are you sitting there? At least, Jacob, is it a different counter from William and Nathaniel? He's facing this direction where he can see. Now, I don't have a problem with you wanting to sit at a counter either. But could you at least pick one over there where you're facing forward and you're not sharing a counter with one of them? Will that work for you? Okay. Now, do you remember the words reactant and product from middle school? Okay, I got some nods out there. All right. This side is referred to as the reactants. And we're going to use these words lots when we use the chemistry section of the course. It's on the left of the arrow. This side is the products because it's on the right side of the arrow. Okay? So, are we going to add the heat to the reactant side or the product side if we need to heat them up to get the particles to move faster and spread out? I hear the reactant side. That's exactly right. So, we're going to say plus heat over here. Okay? What? We're going to do that later in the semester. Okay? Now, when heat is added to the left side or the reactants, it is endothermic. Okay? Anytime we add it to the reactants or the left side, it's endothermic. Now, what does it mean to say endothermic? Heat is what? What's endo mean? Inside. So that means absorbed. Okay? Heat is absorbed. Now, if heat is absorbed, how's it going to feel to us in the lab today? Is it going to feel cool to the touch or is it going to feel warm to the touch?
No, it's going to feel cool.
Feels cool.
Because it pushes the
Oh, we
water
can
out.
have that girl burning herself.
No. You're not going to handle anything that's going to feel cold. Feel hot. It'll feel warm in the cups, but it's not going to feel hot enough to burn you. She touched hot metal after you've been heated with a Bunsen burner. Or the ceramic. I don't really know what she touched, to be perfectly honest with you.
What lab was it?
They used a crucible, which is a piece of ceramic, and they burned magnesium wire.
They allow you to do that.
But we do in chemistry. They're actually going to make salt also, most likely. Well, I told her lab partner to handle the rest of it. I don't think she ought to do it for a while. All right, catch up with me and we're going to review what we wrote down.
We don't practice this.
Yes.
No, it's up there. No, it's the lab.
Up there, like on the board. Not really.
You know, worksheet.
You asked for the graph.
Oh, we're graphing. Okay.
I like that. Cool to fill that big part, just start fourth up. See that right here.
All right, we all caught up? We're going to need white. I think we're all there. All right, so if we look at that liquid, particles are close together, right? We want them to do what? To be spread out. So we need the particles to move far apart. How do we get the particles to move far apart?
Add heat.
We got to add heat. If you want to add heat, what side do you add the heat to? The reactants or the products?
React.
The reactants. If you add heat to the reactants, are we absorbing it or are we releasing it? You're absorbing it. So if it's added to the reactants, we call it what? Endothermic. Okay? Is everybody with me on that? If it's endothermic, it feels how? It feels cool. Are we there? Okay. Now, we need to talk about how evaporation and condensation are similar and how they're different. And then we'll do condensation. Now, how are evaporation and condensation similar? That's an easy one. They both do what? They change from a what to a what? They both change from a liquid to a gas. Okay? That's how they're the same. Okay? They both change from a liquid to a gas. Oh, did I say that? Oh, we're talking about evaporation and boiling. Okay? How are evaporation and boiling similar? They both change from a liquid to a gas. But they're also different. And we can usually come up with a decent list of how they're different without me revealing the list. Tell me something y'all see in boiling you don't see with evaporation. Bubbles. Well, bubbles. Evaporation doesn't bubble. All right? Tell me something else we know. All right, what about the heat? Where do you heat for boiling? But where?
From the bottom to the top.
All right, so boiling, we heat at the bottom. Where does evaporation usually heat from?
Top.
The top, okay? Generally, when we heat for evaporation, like right now, it's, I don't know, probably in the 50s. It's temperature outside. 58. All right, if I stuck a pot of water outside, would it eventually evaporate?
Yes.
Yeah, if I left it outside, it would evaporate. Wouldn't be very fast, but it would evaporate. Now, if I put it out in the sunshine in the summertime when it's in the 90s, it would evaporate much faster, right?
Yeah.
All right, a lot faster. But it will evaporate also. Where does the source for the heat come from that evaporates?
The sun.
The sun. So evaporation comes top down. Boiling comes from the bottom. Okay? Let's see. What else can you tell me about boiling and evaporation? Which one's going to be at the warmer temperature?
You don't need to boil it up.
Okay, so what can you tell me about the temperature?
Boiling is hotter.
All right, so the temperature is going to be warmer on boiling than it is for evaporation. Which one's going to have a specific temperature? All right, so what would the boiling temperature be for water? Anybody tell me?
400.
That's a little high, Gravel. 400 is a little high.
212.
212 is on what scale?
Fahrenheit.
What's the Celsius temperature? Anybody know?
30. 60.
Anybody know Celsius?
Not really.
That's 100. 100 degrees Celsius. So boiling has one temperature. Does evaporation happen at one temperature?
No.
No, that happens in a whole range of temperatures, okay? Doesn't happen at one particular temperature, all right? Now, where does evaporation occur in the liquid? At the top or throughout? Where does evaporation occur in the liquid? At the top or all throughout?
Top.
At the very top. Where does boiling occur in the liquid?
All about the.
How do you know it happens all throughout the liquid?
Because they're bubbles and bubbles.
You see the bubbles, okay? It comes from the bottom, but you see the bubbles, okay? So, you need to make a chart because I'm going to ask you these on the test, all right? So, evaporation can happen at any temperature. It doesn't even have to happen at a high temperature. Any of y'all ever have ice cubes in your freezer?
Oh, yeah.
And the ice cubes suddenly get smaller?
Yeah.
What happened to the ice cubes?
Evaporate.
It evaporated. Okay? So it doesn't have to be a high temperature. It can be at a range of temperatures. But boiling has to happen at one temperature. It doesn't happen at any other temperature. It has to be one specific temperature. Okay? And I warn you, these are for response on the test Friday. Now, evaporation only takes place at the surface of the liquid. It does not happen all throughout the liquid. It's only at the surface. Boiling happens all throughout the liquid. And we know this because we see the bubbles going all the way through the liquid, coming from the bottom through the liquid to the top. That's also how you know it's convection, because you see the bubbles moving through the liquid. With evaporation, where does the heat come from? Comes from the top. With boiling, the heat comes from where? Comes from the bottom. Okay? With evaporation, I say this to people all the time. There are no bubbles in evaporation. If you see a puddle in the summertime that has bubbles in it, don't step in it. Okay? Never step in a puddle that you see bubbles in.
Oh, yes.
All right? It's not acid. All right? But in boiling, you see bubbles. All right? All the time, people get burned in Yellowstone National Park. You see water with bubbles in it all the time. Those are thermal pockets. That water is boiling. Don't step in it. Don't put your hands in it. Don't put anything in it. When you see water with bubbles in it, it's boiling. You don't step in it. You don't put anything in it.
I'll put spaghetti in
Well, you put spaghetti in it, probably cook it. All right? And of course, you all said that one at the very first. Particles move much slower in evaporation because the temperature's lower. Questions? Do I need to wait on you to catch up? All right, we're giving everybody enough time?
Yeah.
All right, looks like I have now. All right, so condensation. Same concept, except this time we start in what state? What state do we start in? Start as a gas, and we become a what?
Liquid.
We become a liquid. All right, so we want to figure out what happens to the heat here. We start out with our particles all spread out, and our particles have to become very close together. All right, so the particles are spread out. And we want them to get closer and slower.
You add cool air.
All right, we can't add cool air. Okay, it's always about the heat. Does the heat get added, or do we remove heat? Do we absorb it, or do we release it?
Release it.
Okay, so if we absorb it, I go back for just a second. Don't panic on those of you who are still writing. All right, if I absorb it, what did absorbing it do? All right, it made the molecules do what? Move further apart and go faster. So if I want them to get closer together and slow down, do I want to absorb the heat? No, I want to do what with it? I want to release it. Okay? So this time, I'm going to release the heat. Okay? So this time, we're going to release the heat. Okay, releasing the heat allows the particles to slow down. Now, notice where the heat's at. Okay, that's right. If heat is on the right, it is a, let me say and, exothermic reaction. Okay? So, what does exothermic mean? Okay, so does that mean absorbed or released? Okay, so heat is released. So how is that going to feel in a little while if we have time to do the lab today? It's going to feel what? That's right, it's going to feel warm. It will feel warm. Now, and that's one of the things you have to do with the two reactions you're going to mix today. You can't mix them and immediately say, oh, it doesn't have any temperature at all, or that. You've got to give it a couple minutes to have time to react, okay? So it's got time to either get cold or it's got time to get warm, okay? Can't just mix it and 30 seconds later go, oh, it didn't change temperatures, okay? You got to give it a minute to do its thing. Okay, so anytime you want the particles to slow down and get closer, the heat has to do what? Be released. And that will make it exothermic. So we want to use the same thought process to do freezing and melting. Okay, it's the same thought process to do those other two phase changes. Okay, what are you doing? I'm beginning to agree. Between the amount of paper he's balled up and wadded up over there, and now it looks like he's got notes written on the paper he's holding up, like he's sending signals across the room. All right, is everybody caught up? All right, so if we go back and do melting and freezing. Whoops, too far. All right. So melting. What state does melting start in? Think about an ice cube. What's an ice cube start as? Starts as a solid. Okay? So we start as a solid. And we change to a what?
Liquid.
Okay? Change to a liquid. All right. So I have my particles all stuck in a fixed pattern, all lined up in neat little rows. And this time, they're just going to sort of get unorganized. All right, so what do I want them to do? Do I want them to move more and get further apart, or do I want them to get closer? Okay, so I know I want them to move more, and I want them farther apart. Okay, so if I want them to move more and I want them to be farther apart, do I have to add the heat or do I have to remove the heat if I want them to move more and get farther apart?
You have to add.
What do you think, Jamie? Okay, add is right. Okay, so we have to add the heat. So if Damien and William say add the heat, do I add it to the reactant side or do I add it to the product side if I'm going to add the heat? All right, Nathaniel says the reactant side of that is correct. So I add it over here. So if I add it over there, is it endo or is it exo if I add it to the reactant side? Is what? It's endo. All right, that makes it endothermic. Because y'all said it's a reactant. Y'all said add it to the reactant side, so that's what makes it endothermic. So how's it going to feel in the lab today? Since y'all said it's endothermic. It's going to feel cold. All right, so freezing. Freezing would start in what state?
Liquid.
All right.
Liquid to solid. It would be unspread out and then it would go to deep.
It would what?
It would stop moving and get closer apart.
All right. So you've said enough. You two hush. Y'all have said enough. All right. So we're changing from a liquid to a solid. Jacob said they're going to get closer together because I know what he meant. All right. William and Jacob are not answering anymore. So are they getting slower or faster? You're not answering. You're not either. They're getting slower. Okay?
You can't answer.
Nathaniel can answer. All right, closer together and slower. So, in order to get closer together and slower, what do we have to do to the heat? Do we have to add the heat or do we have to remove the heat? Okay, we have to remove the heat. All right, so if we remove the heat, does the heat get added to the reactant side or to the product side if we remove the heat? All right, we got to add it to the product side. So plus heat is over here on the product side. So if I make it a product, is it endothermic or is it exothermic? It's exothermic. Because y'all said it was a product. You with me, Ashanti? Are you with me? Yeah. Questions? I'm not sure John and John are with me. Although I'm trying to figure out if Mr. Hernandez is this grumpy in all of his classes or if it's just mine.
He tripping. Are you good now?
He's standing up in the
I thought you were standing in the space.
Do you look more pleasant in your other classes? Or do you look happier in your other classes? You having a bad day?
The hood, his hood blocking Jesus.
I've been in school. I'm 49. I've been in school for 45 years.
I love this one.
Yeah, I don't know what I'm going to do when I retire.
You don't know?
I really don't.
I feel like
I've been in school since I was 4 years old. I went to school for 12 years, 13 if you count kindergarten. I did 4 years of college. I will have taught for 30 years. I don't know what I will do without a bell schedule. Can you imagine my life without bells ringing?
I'll bet you your first day of retirement, you're going to get up and go to a different room in the house.
No, I'm not worried about summer. But, you know, when August starts up, imagine.
She won't come to school her first day.
No, I'm not. I don't know what I'm going to do, but it won't be that.
Become principal.
No.
And then she's going to get up. I got to go to work. I'm late. Oh, no.
All right. All right.
Well, how do you do that teach? Like,
Retire? 30?
This
28?
is
All right.
So you'll retire when we graduate.
When sophomores graduate,
You said you went to.
I'm on 28.
Oh, you're
So
on
I'm on 28. So
So you'll
y'all, I'll be on 29 when y'all graduate.
I believe you. Keep going.
I'll make it. Unless I decide I want to, well, 6 times, then I could, well, we all do, but I plan to do the full 30. So when you look at phase change graph, looking at that, draw it, leave some space. Do not draw it really teeny tiny. Fourth period yesterday yelled at me and said, you didn't say to draw it really big, Miss Wall. Didn't I just say that?
Yes.
Okay?
I said, don't draw it.
I said, don't draw it teeny tiny. All those lines, I'm going to explain what they are and write stuff on them.
So pretty much use one whole page.
I would use about a half a page. But I would say half a page would be plenty. If you don't write real big, a third of a page would be plenty.
All right. Really.
That don't sound half bad.
That's Emma. At least I
All
know.
these students are.
Hmm?
How do you know these students? How do you tell them?
Let me see if I'm right. Yep, I was right. They said you didn't sound half bad, and I said it was Emma. They said, how did we know? I said, let me check.
Sorry.
It's good. You did what?
I'm doing Latin now.
You doing what now?
Well, I'll do Latin.
Oh, okay. She's gonna sing Latin for us now.
In Latin.
Right.
Does she know how to speak Latin?
All right, have we had time to draw it all? All right. Now, for those of you who never study, you have 5 or 6 questions on this graph on the test. I've got a graph, looks just like it, okay? I'm going to ask you what these points are on the test on Friday, okay? I can't be any more.
I called it. I called it.
We have the test every Friday.
We do not have a test every Friday
This is the first Friday we've had this.
in a while. Not everybody, but in a while. But the energy and heat test just happened to fall on this Friday. All right. Now, looking at this graph, okay, it's a phase change graph. So, first of all, what have we said about temperature changes in phase changes? Do phase changes have temperature changes? No, that is correct. They don't. So, this right here is a phase change. This is a phase change. The flat spots are our phase changes. So when we melt, when we freeze, when we boil, evaporate, or condense are the flat spots. Okay? Everybody hear me say that? The 4 phase changes are the flat spots. Now, so what are the places where the graph goes up? No. Well, yes, temperature changes, yes. But they're just states of matter. They're just the phases. They're the solids, the liquids, and the gases. So, for the sake of being able to talk about what they are, I'm going to label this as A. Well, let me change color. Let me make this A, B, C, D, and E. Okay? Okay, so A, being the lowest temperature, would be what state? What state would have the lowest temperature? Solid, liquid, or gas?
Solid.
That's right. So A is a solid. All right, C would be what state?
Liquid.
And E would be what state?
Gas.
Yeah. Now, what's another name for gas that sometimes we use? Starts with a V. Vapor. Okay, vapor. Sometimes we use vapor. Now, because the graph goes up, and this is temperature, right? technically the solid is being what? Not melting because it's not flat. It's being heated, or you can say being warmed. Now, if we drew the reverse and the graph was going down, you could say the solid was being what? Starts with a C. Cooled. Okay? But because the graph is going up, the solid is being heated. All right, so what's happening to the liquids as the graph is going up?
It's being heated.
It's being heated. Now, what about the gas?
Being heated.
It's also being heated. Now, I point this out because we need to label the phase changes. Now, we know the B is a flat spot. It's a phase change. But now that you know A is a solid and C is a liquid, what phase change is B?
No,
Melting is great.
I can't answer no more.
Okay, so that's melting. Now, if B is melting, what's the opposite of melting?
Freezing.
So it's also freezing. So B is melting and freezing because it's between the solid and the liquid. Does that make sense? Okay. So for D, we start as a liquid and we change into a what? We're a liquid, we change to a gas, so this would be what phase change at D?
Evaporation.
Okay, evaporation. I heard vaporization, that's fine. There's nothing wrong with it. What's the opposite of evaporation? Condensation and boiling. All of those fit for D. Okay, all three answers are correct. You're going to let somebody in? Oh. All right. All three answers are correct. Questions about the graph? Now, what if, everybody got it? What if I flip it? What I need. What if on the test, I try to get tricky and I do this to you? It's backwards. Does it move anything?
No.
No. This is still a gas. This is still a liquid. This is still a solid. So this still means that's a what? That's still a melting. That's still a freezing. That's right. That's still condensation, still evaporation, and that's still boiling. It moves absolutely nothing for me to draw it backwards. The only thing is this one is cooling, whereas the other one was being what? Heated. You with me on that? All right. Somebody come hand this out to me.
Whoa.
You know, I forgot I had to demo in your class. Should I do leave that? I had to do a demo in your class. I gotta put this back down. The hose on that. Yep. Yeah.
I already did this.
I knew that too much. Yeah, I never.
When?
It was in my packet with Zelman. It was this and like another sheet, and I was like, I guess she stapled it with Zelman's.
Logan.
I didn't send anything to you.
It was, I swear, it was in my packet with
It may have
Zelman.
been, but I didn't send you any work.
Oh, that was weird. But
That's what they do.
have no idea, because I didn't send you any word. I haven't sent you anything. Okay. No, I'm gonna do a demo in a minute. Then you just sit there and the rest of you do the answers real quick. I'm only gonna give you about. It won't go on very far. It just needs to be on a little bit. Let's see what you got. And y'all don't mess with the gas nozzles. Because I'm gonna need them shortly and I need to make sure they're off. Think of that.
Wait, this one, they would be warming at their facial. When solid, or they run, because it says, the letter represents the rain.
Oh, yeah. Yeah, we have to go. So we're. And 1, 2, and 3, they want a number, by the way. 1, 2, and 3 wants numbers, not A, B, or C.
Oh.
They don't want letters, they want numbers. When it says a point, they want a number. Put a unit on it.
My bad.
It's just facts. The only thing I'm collecting for that. Today is the 24th.
What does it mean by, what letter represents crystallization?
Crystallization would start at what and go to what? Do you remember growing crystals in elementary school? You'd have to start as any ideas what state you have to start as?
Oh, I like the.
Yeah, you'd start as a liquid and it would turn into a solid. Y'all stop beating on the lab counter. It's not drums.
Change potential energy. We gonna do?
Think about changing kinetic energy first and then try to do it. It makes more sense.
That's it, sir.
All right, let's see what you came up with. Let's find graph. There's the graph. Phase change graph. Feel them at the output. All right. Come on, today. All right, let me see if I can find mine so I have the questions handy. All right, there it is. Number one, what is the freezing point? All right, freezing point would be where? Right here, right? So freezing point would be 5 what? Degrees Celsius. All right, the next one says, what is the boiling point? So boiling point would be what? 15 degrees Celsius. All right, number 3, melting point. Melting point is back here again, right? So melting point is 5 degrees Celsius. Any questions about 1, 2, or 3? All right, where's the solid warmed? A. Where's the liquid warmed? C. Where's the vapor or the gas warmed? E. All right, which letter represents melting? Melting is B as in boy. All right. Which letter represents vaporization? D as in dog. Everybody okay with that one? All right, so now we're at the one that said potential energy. Skip that one and jump to number 10. Kinetic energy. What was the definition for kinetic energy? In motion. In order for something to move, what do we change to make it go faster? Temperature. So what is changing in temperature on this graph? A will change in kinetic energy. What else? C will change in kinetic energy. And who else? E will change in kinetic energy. Okay, so A, C, and E are the answers to number 10 because what's changing? The temperature changes, so their kinetic energy changes. Now, if we go back to number 9, what is the potential energy that's changing?
B and D.
B and D. Does that make sense?
Yes.
All right. So from there, number 11, condensation would be where on the graph? D is condensation. And then the last one, crystallization would be, if you never did this in elementary school, a lot of teachers don't anymore, but some science teachers still do. You grow rock crystals or rock candy. You start with a liquid. All right? You start with a liquid. You usually put a string with like a paper clip in here. All right? And the crystals grow around it. So you start as a liquid and you change to a solid. So if you start as a liquid and you change to a solid, where does that happen on the graph? B is where that happens. Okay, liquid to solid is at B. Okay, questions? All right, the last tiny little bit of notes we have. And that's what goes to the demo I was setting up back there. All right. The last little bit of notes is on thermal expansion. All right, what is thermal expansion? It's when something increases in size because you do what to it? You heat it. Okay? Thermal expansion is when something heats up or increases in size because you heat it. Now, we have lots of examples of these that we use every day. All right? One of them that y'all might be familiar with are sidewalk cracks. In the summertime, sidewalks get heated by sunlight, and they are going to expand. Okay, their particles move faster, they spread out. If we don't leave gaps about this wide between sections of sidewalk, the sidewalk pushes up against each other and buckles. And so the city has to come along, chop up the sidewalk, and they have to put down new concrete. That's expensive. So we leave gaps every so many feet in the sidewalk so that the concrete has space to expand. If you drive on a highway that's been cemented, they do the exact same thing. They leave cracks, about like that, every so far, so that the cement has a place to expand.
So that's why when we go across this, you.
Yep, exactly. Potholes in roads are another place. Or even if you put drinks in the freezer, same thing happens in both of these. If you put drinks in the freezer, anybody ever put one in there and the plastic, or it explodes. Either the plastic will crack or the bottle, God forbid, explodes. If you have a bottle that it's under pressure, that will happen. Okay? The material in there only has a little bit of space at the top. Okay?
I had like boiling water in water.
Well, that will happen too, but that's for a different reason. All right? If you put a bottle of, let's just say, Aquafina in the refrigerator or put it in the freezer, there's just a little bit of space in there. Do you have enough space for that water to expand?
No.
No. Crack the top, drink a little bit out, then put it in there if you want to freeze it and take the bottle with you all next day. Because if not, it's probably going to split the side and it's going to leak on you all day because there's not enough space. Same thing with potholes in the road. When it's wintertime, it snows, it freezes, it ices, and then it freezes, the water expands, it cracks the pavement or the asphalt or whatever. We drive over it, we break up the potholes or the roadway, and then it creates those giant holes that we drive through. Now, the two applications we're going to talk about today. One you're going to use in lab. The first one is a thermometer. Okay? When heated, what do you see happen? The liquid rises. Now, we don't have any mercury thermometers. We have alcohol thermometers. Okay? I got rid of all the mercury thermometers 28 years ago. All right? Simply because if y'all break mercury thermometers, everybody wants to play with it. Put it in their hands. Mercury will absorb through the skin and give you mercury poisoning. So and you could possibly die. So I got rid of all of those my first year here. Now, the second thing, and I'm going to demonstrate this. Logan, close the door. The second thing I put up here, you have in your house, and I have one in the back I'm going to demonstrate with, is a thermostat. Logan. Shh. William. It's called a bimetallic strip. Whether you have central air, you have baseboard heat, if you have any type of heat that cuts on and off in your house where you set a dial, it's got a digital readout, whatever. If you are able to set it on a particular number, then you have what's called a bimetallic strip. Okay? Now, this bimetallic strip is two pieces of metal that expands at different rates. And I'm going to show you how that works with the Bunsen burner I have set up back there. Okay, but your thermostat does that. When it gets cool, it expands one way. When it gets warm, it expands the other way. Okay, so it can turn your thermostat on or off depending on the heat in your house. Jacob, do you remember what I said? That I didn't mind you sitting there because you were sitting at a different counter and facing forward. Oh God, just turn your hands for a few minutes.
What was that?
The gas is coming on.
You got to get ran out of here. She better like
Wow.
this all on her guy.
You can see about lighting on fire.
I get a safety mattress to light.
You say safety match.
All right, so we have
Safety.
a metal ring and a rod, right? These fit through pretty easily. Works better when both hands on work. Alright, but I can get the ball through the ring without breaking the difficulty. Now, if I put the ball in the ring, what's gonna happen to the fire? What's gonna happen to the particles in the ball?
Expand.
Alright, first of all, the particles are gonna move faster. And as they move faster, they move farther apart, which is what's gonna cause them to expand, right? So as they get moving around in here, takes them a little bit, but eventually, will they fit through the ring?
No.
Mm-mm. So if I try to stick them through the ring, they're not going to fit. I'm gonna wake Bree up before she drools and yelling at us again.
Hurry
Bree,
up.
you awake? I don't want you yelling at us because we let you drool on the disc again. Alright, so does it fit?
No.
No. So if we turn the water on and I cool it back down again, the particles do what? They slow down, they get closer together, and they can easily fit through the ring again. Now, this is the thermostat. Alright, this is the bimetallic strip. Okay, we all have one in our thermostats if we have one in our house. So, your house, let's just say, what temperature you set your house thermostat at?
72.
Okay, 65. That's a little chilly. 72. That's a little warm in my house too. I want mine to about I can't afford it. All right, let's just go with 70. So we got our house set on 70. All right, as it gets cool, all right, the heat comes on. All right. So when the heat comes on, turn it off. So the heat comes on. What happens to the bimetallic strip? Anybody tell? It's bending. Okay. So it bends away from the piece of metal. And it says to the heater, the air conditioner, the whatever, the central heating and air, whatever system you have, your house is warm enough. It cuts off. As it gets cooler in the house, because, as you have it off, the heat cuts off, it starts to get cool, right? It says, oh, I've gotten cool again. I need to cut the heat back on. Heat comes on, warms the house back up. What happens to the bimetallic strip again? It bends back away from the thermostat, warms the house back up to the 70 degrees, and then the heat does what again? It stops and cuts off again. And then the heat cuts off for a while, and the house gets cool again, and then it says the house has gotten cold again, and the heat cuts back on again. And it's a repetitive cycle of on, off, based on that bimetallic strip in your thermostat just bending.
I bet it's tired of it.
Okay? So that's how it works. Any questions? All right. Now, that's the end of the notes that go with heat. Now, do not turn any of those gas nozzles on, because the gas is going to be on to the end of class. Okay? I have to set it for a particular amount of time, and it's just on right now. All right, let's start live, because we've got time to at least do half of it. All right, so hand this out. All right, I'm going to alter the directions in part one. So after Jacob hands it out, I'm going to tell you what I want to alter, because I'm trying to do this so we don't have to clean the glassware. Yeah, I'm lazy that way. Yes, we would.
That's when you got you put fire in your back and it's like a all in your oven. It just leave it on.
It's only my room. The rest of it wouldn't work. It's been remodeled. But it'd be enough to take out the rest of the building.
What, is this room below us?
Mm-hmm.
We got this side included, or like
At least this whole half.
That's a lot. That's dangerous.
Just don't stay on while it ticks down the time. Just leave the gas off. Remember, before it was all on all the time. Before they did the remodel 3 years ago, it was all on all the time.
With that thing, it never even fit.
No kidding.
Like a whole fire department here.
Bro, they would be like the freaking every fire department from here to like.
All right, does everybody have a sheet? All right, so in the top section, it says to fill an empty beaker, 40 milliliters, fill with tap water. Forget the amount in 40 milliliters. When you get your beaker, here, let's just not- all right, I've set it up. Keep going. Not that page. So you have a beaker and a purple cup. Okay, put your tap water in the beaker, but just fill the beaker half full. Okay, measure the temperature. When it says to pour the Epsom salt in the beaker, I want you to do it backwards. Pour the water in the purple cup, because the purple cup we're not keeping, we're just throwing it in the trash can. The water will not mess up the beaker, and we don't have to wash it. If you pour the Epsom salt in the beaker, I gotta wash it, okay? I don't wanna have to wash glassware. So pour the water in the cup, do the experiment in the cup, and we can throw the cup out. You got me on that?
Yes, man.
Okay. Now, when you're finished with part 1, if we have time, we'll do part 2. Do not, you hear me? Do not pick up these cups unless you have completed all of the front side. And then I will give you the supplies for part 2 if you've completed the front side. Everybody got it?
Yes.
All right. If we don't have time, put your papers on the stool and I'll hold on to them for tomorrow. Okay? All right. Part 1. Get going.
You sweet?
I've been on my phone. I get some good sleep. I'm not going to go to sleep.
Yeah, this is hot.
Alright, guys. We can send it to 2 parts.
You left the matter.
Yeah, it won't hurt anything. Just leave it there. That's because I just took this apart.
That's the thing you left in the gas out.
Yep.
You feel something in there, something.
Man, I woke up this morning. Yeah, I forgot to turn my phone last night.
My son does that, I think, every day.
No, because I was on the phone with my mom, and then I fell asleep.
I'm fine.
All right, get to work. Everybody ought to finish the front side today.
Alright.
Those are all bits. Yes, you do. Your thermometers are up here on my desk, so they stay safe. Thermometers are up here on my desk.
Don't drop it. I used to have a Mercury.
Put 2 and 4 cup. We'll play with that when we do waves. 3 units away.
3 units.
After electricity, magnets, and then waves.
We got first. This for us, we can just
Thermometers are on my desk.
We get big.
Just go grab one out of the cabinet back there.
This smallest thing ain't moving.
They're gonna be about a little higher than your waistline, Sacramento. And on the left side. Got it? Got it.
So what we do is pour this water in the cup, right?
Yeah, pour it into the purple cup after you got the test.
Now that was.
I ain't got any more.
I got 20. I'm gonna say 20.
And don't shake the thermometers before you smash it into something. Why do you have the beaker sitting in the bottom of the sink?
You got these thirsty.
Stir the Epsom salt gently with the thermometer. Gently.
So there's what? Oh, water in there. I was.
No, because what we did was actually when we first go ahead and read the water. It was
Alcohol.
the same anyway. They have 4 drops. They have triple drop probations of water.
What's the way that word? Clap.
Bless your mouth.
What?
Hey,
No,
Say this slowly.
I was like, no, it's like, look, that, no, he said, yeah, man.
You know how it is, you know, in Iceland, they have such this
That's why I thought it was.
It's what
salt
they make
getting
it like water.
It's not dissolving.
It won't dissolve.
It's like,
I thought it was something.
It's only going to dissolve partially. It's not going to dissolve a lot.
And what about dirt?
Did you get over or colder?
Oh, I got, mama said that. It got colder.
You write that down. You can also feel the cup. Feel the outside of the cup. Did you get warmer or colder? Then write it down. In the box it says observation. Why are you playing insane?
So that means it's going down.
Why is that big?
That's what it is.
That's what it is. If it's so.
Oh, Epsom.
What?
Stop it. That's scary.
Oh, just, hey, breathe. And I'm,
This most definitely ends up on this got cool. Look at
William.
And that was cool. It got He always moves in the same direction. What is that direction? Out. No, in. When it's cold, you have to close it. No, he tries it out. He tries it out.
You need to pump it up. That's the opposite.
If I got this ice on my hand, it's gonna travel out into the ice.
All right, has everybody made their observations with their Epsom salt?
Yes.
Got their two temperatures?
Yes.
You have to have at least that part done before you leave. Because we've got about 5 minutes left. Because if you don't have the two temperatures in your observations, you're wasting my supplies. That's what I want you to tell me. Do that based on feel.
He travels.
I drink that.
He
What
travels.
did you know? Write it down today.
I know it's actually because when it gets hotter, it's in that.
Don't do that. I thought I was this one.
Someone's supposed to know.
This one. He travels in or out.
It doesn't travel in or out. It travels from warm to cold.
So what is it
All right, it's 1:16 noon.
There is nothing else.
Your thermometers have to go back in the thing in the front. You can throw the cups in the trash can.
Where did they get it out first? Where did they get the water out first?
Are you missing your?
He got because it knows your exo.
No,
you throw it away.
No, that's a salt.
Don't pour it.
That's good. That's what
It's gonna clog up the drain.
It's not going to plug in the drain. You're going to go in the trash.
Let's say,
Not going to hurt us.
I got.
So we can't pour it down the
The trash can is all I care.
You know how it's hot. The part of the seat up, heat up, you get cold.
Beakers go back up
You know
front.
what I'm saying?
Thermometers go in the stand. Purple cups go in the trash can. If you wash down the drain, you better get all that salt out of my sink. You can throw the entire thing in the trash can. Put it on the stove. Wash all that salt out of the trash can and you pour it down the drain.
Done.
Purple cup goes in the trash can. Beakers up front. Thermometers in the stand. Put your paper up front and I'll hang on to it for you. Stop doing that to the handle. You put all of it in the trash can for all I care for you.
You're throwing it away. Quit washing it out.
Over in the trash.
It's okay.
Can I have this one
Dang, nice.
Good job, you put that big one.
Dang, Bree. She's going, man.
Don't.
Just dump it.
Everybody got their beakers put back? Thermometers? I didn't say dump the cup. I just said put the cup in there.
I wanted to dump. I want to see what it looked like. I want to see the look so good.
Put my equipment up. Papers up here on the stool. Once you got cleaned up, you can go.
You don't remember that. I'm calling your number. Maybe swole.
Yeah.
You would have did it too.
Yeah, as long as I have it tomorrow afternoon. If I don't have it tomorrow afternoon, though, it's zero. Hey, it's zero.
I gotta leave. I gotta go to this washing machine.
They ain't that all the juice.
So I might show myself, I swear.
Say what?
Yeah.
And then you pull. Here you go.
I'll make sure everything's picked up first.
No.
Thank you, sir.
I'm in wall.
Bye.
See you tomorrow.
What's the name of that red thing? Did I miss it one?
It has carousel